you will get, you start from the beginning. Up, left, like you read in newspaper. So it's going to have manganese 2 plus 2 waters, plus left, plus Br2. That will give you manganese dioxide plus 4H plus 2Br minus. Okay? So that's balanced, if I order correctly. That's balanced in acidic solution, as we call it. And we want it basic. We don't want H plus there, we want OH minus. And the rule is we're going to use so many hydroxide ions as protons in both sides. Because if I add the same number of ions in both sides, then I don't disturb my already balanced equation. How many I'm going to add? Hydroxide, because I want in hydroxide to be. I want to see hydroxide, no H plus. As many as there are here. So I'm going to put 4 here and 4 there. That way it remains balanced. Yes? I don't have space. I could put it there or there. Doesn't matter. It's okay. Sloppy. Really sloppy. Should have put it here and there. It's okay. Now, look at this. When you have H plus and H minus together, they will not really like to be together. They just don't like to be together. Immediately they will react and they will give you what? 4 waters. So this is gone, and get you 4 waters. And because you have 4 waters here, 2 waters there, this 2 goes away, so I completely erase it, and this 4 becomes 2. And then you can write the last, final one will be bromine. After we did these things, manganese 2 plus 4OH minus, manganese dioxide plus 2Br minus plus 2 waters. That's it. We're done. We always give you to calculate the empirical formula of something. We always do that, right? So you should know how to do an empirical formula calculation, right? How to do the empirical formula from percent analysis or whatever, right? I don't want to go into that. We can do some other things immediately, right? Okay, let's do another problem. It's a stoichiometric problem. Made it this morning out of the oven fresh. Just quick. Okay, let's say that we have this chemical equation. A gas plus 3 B gas gives you C gas. Okay? We got it. A and B gas reacts in this geometry, 1 to 3, to give you C gas. You already know how to do problems with grams, polarities, all kinds of different things, molecules, moles, right? This, how much of this you have, it can be expressed in many different ways, correct? Polarity, just polarity, different types of concentration, moles, molecules, grams, kilograms, blah, blah. If it's gas, it could be volume. It could even be current, even in pressure. Usually we use volumes. Could even be pressures. Usually we use volumes. And we start talking about grams or molarities or whatever, moles or molecules, we can talk about volumes, like cubic centimeters or milliliters or liters. And as long as the volumes are measuring the same temperature and pressure, then the ratio of the volumes that these react with and they give us is the same ratio as the coefficients. It will be that, in other words, 1:3:1. You understand why? You want me to show you why? How many people want to show you why this is true? Let me see your hand. Oh, you're not interested? I'm not interested. So we'll just solve it. If you want to know why, at the end, I can show you. So let's say that you start with 2 liters of this and 9 liters of that. And the question is how many liters of this you get. Okay? I'll give you a few seconds to do it. Okay? Very easy. Look at it. Yes, it is 9. 2 liters and 9 liters of it. 2 liters of A, 9 liters of B. And they are measured at the same temperature and pressure. Both of them. So how many liters of C I will get? This reaction is complete. Good job. You almost broke your back. Okay. How many people are confident they know the answer? Let me try. Look how you think. 1, right? This is 1 there. Can you see it? 1 molecule of this reacts with 3 molecules of that. Or we can say 1 mole of this with 3 molecules of that. Or you can say 1 liter of this reacts with 3 liters of that. Yes? Okay. If 1 liter of A reacts with 3 liters of B, 2 liters of A will require 3 times more. Isn't that right? So how much will it require? 6. What do I have? Okay, immediately, when you see that you have more than what you need, on the top of there, you say that is in excess. And therefore, this is the limiting reactant. Immediately, before you forget. Right? Now, since you know the limiting reactant, you will base your calculations how much product you will get on this, not on that. On this, not on that. Yes? So, from the equation now you know that 1 gives you how many? 1. Therefore, 2 will give you how many? That's it. So you will get 2 liters. You answer the first question. Now, when you do reactions, you don't always get what you predict from the paper. Because when you use these gases A and B, they're not 100% pure. You think it's this much, but it's not that much. That volume can be due to other impurity gases. And you will not get as much as 2 liters, you will get less. So let's say you got, so this is theory, this is cartoons. This is a cartoon here, it's theory, according to theory. Like I said, these are not 100% pure, so you get always less. So let's say you got, 0.5 liters. Actually. What is the percent yield? How much is the percent yield? Huh? How much? 25%. Everybody got it? How many people want to explain to you? It's 25%. Raise your hand. Okay, so most people understood. Why is 25%, right? How many people want to explain why is 25%? Raise your hands. Okay, so you know, you guys. Good. How much of B gas, how many liters of B remain unreacted? Some people say 3 liters. You want me to explain it? How many people want me to explain that? Well, look, we said that we base our calculations here, right? This is eliminated, this is gone. So if this is gone, let's see with what, how much it reacts. We said that 1 reacts with 3, 2 reacts with 6. We have 9, how much remains? Right, you got it now? Huh? Yes? All right. You see what's easy, wasn't it? Yes? Okay, let's go to the next one. Let's do this one. Let's do number 24. Try to find meaning in everything you do. There is a meaning everything you look and you hear around you. Until you find the universe within you, the whole universe within you. Try to understand everything that is happening around you. Why? You ask yourself why. During the break, I will tell you why this is black. All of the Cretans, for thousands of years, they have this black. Why this is black and why these things are going down? It's always an answer. Why I'm wearing these boots, particular ones? There's a meaning for everything. Okay, try to do it. Try to start doing it. How do you start doing problems? You write down what the problem is giving you, what it's asking you. With symbols. If you don't do that, you cannot work. So write down what you know and what the problem is asking. And list that. Okay, let's start working on it. The first thing you notice is that you want to make a solution with a specific molarity. So here is, this problem is talking about molarity. Well, if you want molarity, you will have somehow to make it appear, abracadabra. And it won't appear just like abracadabra, you have to make it appear. Right? So, let's see if we can make it appear somehow from what we know. So we start with what we know. What do we know? We know that we have what? We have 50.6 grams of salt per 100 milliliters of solution. Don't you think if you have so many grams of salt per so many milliliters of solution, you already know the molarity of the solution? How? Well, the grams can become moles. You know the molar mass. You just divide the mass in grams by the molar mass, which is grams per mole. What you will get is what? Moles. Moles of salt. Isn't that right? And that's per 100 milliliters. Well, you divide by 10, and you make it per liter. So really, from this one, you can get what? The molarity initially, the initial molarity of the solution, because you want to make another one from it. Usually you add water to make it less concentrated, or sometimes you even take water out, make it more concentrated. At this point, we don't know what we're doing. Take water out or in, we do not know at this point. But this is the molarity of the original solution. Do you realize that? So I'm going to put it MI. MI of the salt, right? The molarity, how many moles per liter? If you do what we said here. Right? How much comes to be? It comes to be in the calculations 2.83 m. That's the initial molarity. Then, from this solution, which is this molarity, and what volume? Initial volume. What? How much is it? We're looking for the initial volume. That's what we're looking for, right? So this is question mark. That's right. With what initial volume we should start at this molarity? What is we're making? A solution, right? So the final solution, it has what? What kind of molarity it has? 0.25 m. And what volume? 400 milliliters. It's almost done now. Right? So we start with this solution, with this molarity. We want to find out what the volume has to be. In order to make a solution with this molarity, that's the final solution, that will have this final volume. Correct? It doesn't really tell you what to do, but basically, you know, it's an aqueous solution. You will use water, right? Or take water out to make it happen. So what happens in these dilutions or concentrations, you make the solution more concentrated or more dilute, you put water or take water. That which remains the same is what? The amount of solute, the salt, will be the same. The number of moles of the salt will be the same, yes? So we have this relationship, molarity of initial solution times volume of initial solution. That will give you the number of moles if volume is liters. If the volume is milliliters, it will be number of millimoles of the salt. That should remain equal. It doesn't matter how much water you take out or put in, it will be the same with the number of moles, molarity final times volume final. If volume is in liters, it will be moles. If volume is in milliliters, it will be millimoles. It really doesn't matter. They have to be all the same, yes? So from this one, you can solve for VI, which we want to find, and will be V final times what? Molarity final divided by molarity initial. And because this is in milliliters, how much is that? 400 milliliters. Because this is in milliliters, this will come out in milliliters also. So if you put the values, you will find out that it is 35.3 milliliters. Original solution. Original solution. So you go from this to that, that means you have to add what? Water. How much water do you have to add? Even though it doesn't ask you. Right? 400 minus 35.3, that will make whatever. Milliliters of water added. Right? You can do that. That's it. You're done? Any questions? How what?
How do you know grams per mole?
Density.
Got to do some more reading. This is something very general. Pay attention to it, at least now. Number of moles is equal to the mass in grams divided by the molar mass, grams per mole. Grams and grams goes away, and this becomes moles. Yes? Number of moles, mass in grams divided by the molar mass in grams per mole. Yes? Also, number of moles is equal to number of particles, whatever they are, divided by the Avogadro number. Right? Also, it is volume divided by the molar volume. Whatever the volume is per mole, at the same temperature and pressure, if you divide the volume, these volumes are made at the same temperature and pressure. If you divide the volume, divide by the molar volume, you'll find the number of moles. So it's this way, that way, that way. Do you remember anything else? What else? Can we write? Huh? It's not important relationships, right? You should remember them. Okay. Are you holding good? Or you get tired? You're holding good? Yeah? You like problems? We'll go to multiple choice. Huh? Problems? Huh?
How's your arm?
No? I'll take your headphones away. Try to stay away from things that they take your headphones away. Here's a monster, it's coming out. Look at this. Woo! Where are you looking? The monsters are not out there. You know where they are? Where are they? Look at this general things that you will need for your exam. Look at these general equations that are very useful, okay? Of course you know that, right? Then there's another one.
Why did you do that?
How many people saw this for the first time? These three ones here. Let me see your hand. How many people see that for the first time? See, many people don't know this. And it's good rules to know this, okay? So these are very general rules. They are very helpful to know this, okay? So let's say that I give you this kind of reaction. I have a salt, metal, some metal from the periodic table. Here is some anion. And I have one metal and two anions. That's a salt. You can imagine, like zinc chloride, something like that, right? And then I have another salt with a different metal, prime, three of them, and then I have a different anion, that's two of them. Fill it in and and balance it. Fill in and balance. You know how to do the hard thing. It's an easy thing. When it's complicated, element, simple. This is M, A. M prime. So why not do this? Okay, this is the way you think. Look, when you have a salt, you always have the plus part on the left, the minus part on the right. I don't mean it's plus one, minus one. I just say part, okay? The plus part here, the minus part there. So, the salts that they will form will be this plus with this minus, and this plus with this minus. Don't you agree? Yes? So, this M now we'll go with this A prime, and because this metal gives you 2 there, that means it's going to have a 2 here, right? And with this A prime, because you see 3 there, that means it will be 3 there. Is that true? How many people want to explain it? Raise your hand. Yeah? When you have, let's say, barium phosphate. Barium phosphate. Barium phosphate. Metal, anion. Second group, 2 plus. Phosphate, 3 minus. What do you do? Isn't it right? So you write barium phosphate. Isn't that right? I didn't do anything else. I just did that. Right? And you do the same thing for the other one. It's going to be M prime. Same logic. M prime A2. So now I want to balance it. 3M, 3M, 3M. Right? And what else? Three M here, you put 3M there. What else? Huh? 3M prime, 3M prime. Is it correct? Huh? Correct. Okay. Should we go another problem? Who have a break? What do you want? How many people want a break? Raise your hand. How many people they want to go on? Raise your hand. That's why you see the world the way it is. You're in a hurry for worry. Where are you from? We don't even have control of our breath. Do you know that? When you go tonight from this room out, think this way. That way you will dissolve your distress about your finals. Say to yourself, do I really have even control of my breath?
Do you know some people, they cannot finish their statement? They had a heart attack, and they're gone. They just cannot finish the statement they're trying to make. Some other people, they don't have time to cross the street. They think they can. They are not drunk. They are very strong. They have muscles like a giant. But they never make it across the street. You know why? Because someone was drunk and they thought he was not drunk. And that drunk driver hit that person and killed him. That person thought that tonight he would be going to see his wife, his children, but he will not make it. He's not going to make it. And he didn't think of it. That he does not have control of everything. He thought he had control of anything. And that is why he was so angry, fearful, confused, and a great God with him. Because he did not realize that we cannot have total control. Not even on the results or our grades, but even in the process of trying to study to go and take the exam. We have not realized that. And when we do realize that, then you will never be angry, confused, doubtful, weak, fearful anymore. You will be called a self-realized soul. And birth. Know who you are. And whatever you do in your lives, you will excel. You will be a very unique person. Whatever you do, wherever you are. Each one of you has that ability to do this. The ones that they will discipline themselves and think very seriously about this and seek for it every minute of their waking hours, they will accomplish it. There is no way that they will escape not to heaven. No way. Guaranteed. So, the reason we're doing this is because the teacher wants to give a message on campus. And perhaps part of that. And the message is this. You know, the teacher comes from a different country. And in this auditorium, there is a lot of students, a large fraction that they are from different parts of the world. Or their parents, they were from different parts of the world. Basically, we are not from here. All of us, we are from somewhere else. Except if there are some Native Americans in this time right now here. So, even though we say we have made progress, we always use this word. We need to tolerate this, we need to tolerate that, we need to tolerate the different religions, we need to tolerate different behaviors, the way people live their lives, the way they speak, the way they dress, the way they do it, we need to tolerate. Then there's another word which is to accept. That is very seldom to be heard. And then there is another one which is hardly we hear about it. There is such a thing, you can go on Wikipedia wherever you want to look for it. It's called the sword of Damocles. About 65 years ago, humanity created something. And this is called the sword of Damocles. So if humanity has a head, now that sword of Damocles is hanging over the head of humanity with a hair of a horse. And any moment that head of the horse breaks, the head of humanity, you can imagine what will happen. It happened 65 years ago. The sword of Damocles is still hanging there. And unless we forget about this word, because it's not working anymore, if we don't have the power and the willpower, the love it takes to embrace diversity, we at least should accept diversity. And that is why your teacher would like at the end of the lecture, if anyone has his costume, I saw at least one, maybe there's more. We're going to do this every review session, by the way. You come down, and we're going to take a picture right here. And let the message go out as far as God will bring it. So another note I would like to make is, these boots were made by a student of my father. My father was old, about ready to die. Well, he was not that old at that time, he was about probably 80. He died 90 years old, about 80 or 75. And he could not do it. He was making new boots, new shoes, women, children, incredible things. But at that time he was not making it. He was old. I went and I found in a mountain village in Crete one of his students. And he was younger, 20 years younger, and I said, will you please make boots for me? My father now cannot do it. Will you do that? When you do it, it will feel like my dad did it. And actually he did. He didn't have any tools. He just got the materials, he knew how to do it, taught by my dad, and he made these boots. So these boots are for me very significant. I remember my father when he was young, always dressed like this. When we moved to the city, he didn't do it anymore. This one here, I hear stories from my grandmother. They had silkworms taking leaves from their mulberry trees, and my father was listening to the noise they were eating every night, eating the leaves. Then they would take these strings, and from all the process, they would make this beautiful thing that you see here from silk, which is more than 100 years old. That belonged to my grandfather. The reason that Cretans wear as a traditional dress this black is because Crete has a strategic position, and for thousands of years, every empire went to occupy Crete. Just like some parts of the world, they have strategic position, and any empires are created, they want to cultivate them to control the resources. So Cretans were always in war, always fighting, just like some countries even today, because the big powers wanted to cultivate them so they can go and get resources from around the world. And because of that, Cretan homes always had dead people. Men and sons, they were always dead in every house. So this signifies the mourning from every family. Every young man will be dressed like this, signifying that they're always mourning, because every time they have dead people. And these, that they look like tears, if you look at them closely, they represent tears, the tears, blood tears. Because there were so many widows, and in every house they had a lot of people dead, because they would have to fight all the time to stay free. They were occupied one after the other, continuously. So that's a story about the costume, and why we do this thing. Is there anybody play the music here for 5 minutes, something like that? You are here? Come here, Rudy. You have a nice song for us? We can participate. He's one of your classmates.